techniques last time. And we talked about some general comments about atmospheric calibration. We went through some in-scene, ground truth-based thermal calibration techniques, and then some in-scene based calibration techniques for thermal infrared, very specific to thermal infrared. So what I'd like to do today is do one more technique that we use probably more often than anything else in the infrared, and that's the technique based on atmospheric models of Montreal. And then we'll move on and talk a little bit about how we do calibration in reflective wavelength regions. Right? We here at RIT are not, we don't do as much reflective calibration as we do calibration in the emissive wavelength regions, just because that's not where most of our expertise lie. But we do a bunch of it for experiments. I mentioned last time we were going to have an experiment coming up in the September timeframe, so we'll have a bunch of the reflective-based techniques and targets out in the field, so we can do that also. All right, so let's finish up. Oh, actually, any questions on anything that we covered last time? All right, and make sure we stop just a little bit early. So we'll talk about the exam next week too, just to give you an idea of what kind of things are going to be doing. And I've been thinking a little bit more about your question about a formula sheet. All right. So, all right. So one of the things that when you start to try and model the atmosphere, you quickly come to the realization that the atmosphere is a very, very complex thing to try and wrap your head around, and we have to make a lot of assumptions to even be able to start to do this sort of thing. And the first assumption that we really make in most, I would say almost all the models that I'm familiar with that are out there for atmospheric modeling, and there's only a couple that I've actually worked with, Montran and Lotran being the two primary ones. They make the assumption that, as shown in the picture here, the atmosphere is really made up of these discrete, planar, homogeneous layers. Okay? Where, if this is the ground, and this is the first layer of the atmosphere above the ground, and then this is the second layer, and the third layer, and the fourth layer as we go up, in each of those layers, you have a set of gases, atmospheric gases. You have water vapor molecules. You could have clouds that have formed in those layers. But everything in that layer is treated exactly the same. Right? So in other words, in this layer right here, the number density of oxygen, the number density of nitrogen, the number density of carbon dioxide molecules, they're all constant within that layer. Okay? And the temperature, the pressure, and water vapor concentration or water molecules that are in there are also constant within that layer. Right? So it's almost like you form this atmosphere out of, if you had little bags that you could put out there and fill with a certain amount of gas and then stack those bags on top of one another. That's what would form the atmosphere. How else would you do this? I mean, you realize there's no boundaries like this anywhere, right? And this goes from 1 kilometer to 1.4 kilometers, right? So this is a 400-meter layer. And you realize that you don't have these discrete changes at these points in the atmosphere. But to do it any other way would have to be a very, very complicated code. Did you work with other atmospheric codes that actually, didn't make these sorts of assumptions?
No.
I mean, I can imagine there's people who work on these sorts of things, but these are not the things that you're going to run in 10 minutes.
It's certainly not the standard, and it's certainly when you get to the major models that most folks use for forecasting.
Right.
They have to be discrete layers, just if you want to run them in the forecast window.
Exactly. Yeah. So if you wanted to predict the weather for tomorrow, you'd have to start a week ago, even, and then it would all be out of date by the time you got to it.
Yeah.
So because of Well, I mean, let me preface this a little bit. Lotran, which is the base model that Modtran was made out of, the difference between, you probably won't hear Lotran mentioned all that much anymore, but that was a low resolution transmission model. Modtran is a moderate resolution transmission model. Okay, so it's what Lotran evolved into Modtran, probably took over the field maybe 10, 15 years ago. It's the standard everybody uses. It was developed, beginning back in the 1960s. So you could say, oh, well, this was done at that time because computers were so slow and blah, blah, blah. And it's not really true. I mean, computers are infinitely faster now, and these models are infinitely more complex now, that these assumptions still take. Your Modtran runs are taking 10 minutes or so to run, if you've run those through already. I mean, that's, and you're just doing the visible portion of the spectrum, so you don't have any of the thermal stuff's turned on and running in the model. So, but you're not doing multiple scattering. Is that true? In your card deck, multiple scatterings been off, which actually increases the runtime a lot more. So you can imagine if you had a model that did not make these assumptions, and you had to have all the flows taking place between layers and molecules exchanging over and currents going in the air and eddies and all that other stuff, it would just never run in a reasonable amount of time to use it. So we're stuck with these layer assumptions, at least for now, until somebody comes up with a better computational method that we might do this with. And I don't know that that's coming anytime soon. So how do we deal with that? Well, you can actually break this problem down very nicely when you make these layered approaches, in the sense that if your sensor's sitting up here and you're looking down at the ground and you're looking through an atmosphere, well, your path radiance, your upwelling radiance, is a combination of the upwelling radiance that comes or originates in each of those layers of the atmosphere due to scattering of solar photons, due to self-emission of the photons in that layer. And you sum those all together. Well, you have to take a look at that and say, all right, well, what does that really mean? Well, if let's say this is the last layer of the atmosphere, you're at the edge of the Earth's atmosphere, you have a satellite-based sensor, for instance, and this is the last one that you defined in the model. Well, the path radiance originating from there goes directly to the sensor. Well, if you go to the layer right below that, that layer has to go through, or the contribution from that layer has to go through the layer above it, right? So it will go towards the sensor, but it also has to be attenuated by the transmission of the atmosphere that remains above. Right? So this would be LU from the topmost layer. This would be LU from the second to the topmost layer times the transmission of the topmost layer. If you went down to the third layer here, this would be the LU that originates from that layer of the atmosphere through the transmission in the layer above it, through the transmission in the layer above that. So you would multiply these transmission terms together as you would propagate that energy up through the atmosphere. So the total transmission, if you want to think of it that way, from some point in the atmosphere up, is the product of all the transmissions from that layer to the sensor. Okay? So that's the layer assumption that's made in all these models. All right, so the transmission through any layer of the atmosphere we know is the number E to the number density of the molecule that we're looking at. So here, K is the molecular species that we're concerned with. C is the absorption cross-section of that particular species. And then Z is the path length through the ith layer of the atmosphere. So I refers to the layer, K refers to the molecular species that we're looking at. So the transmission due to a particular molecular species in the ith layer is E to the product of the extinction coefficient, the product of N times C times the path length. All right, so if we wanted to go ahead and then come up with the total transmission, so transmission through the ith layer along a path d sub I at wavelength lambda, right? And these are going to be wavelength dependent you would take the product of all those transmissions for that kth species up through the layers up above that point in the atmosphere. And you would do that for all the species and put them all together. Right? So you'd have a certain transmission due to oxygen, a certain transmission due to nitrogen, carbon dioxide. In Montreal, I believe there's 8 molecular species that are present in each of the layer. Their number density is controlled by the pressure at that particular altitude. So to go ahead and then come up with your radiance, right? Let's say we're still looking in the thermal number here. The radiance reaching the sensor is your black body temperature of your target at a particular wavelength, times the emissivity at a particular wavelength. There should be a lambda emissivity there also. Times the transmission, the Tau2 term, through the atmosphere. So through all the layers of the atmosphere from I to N, where there's N layers defined. Right? And then the individual transmissions for each layer, which are each another product term of all the transmission due to each molecular species. So for each layer I, you need to compute this product for the 8 gases that are inside of Montreal. And then each of these tau sub I terms, you need to multiply those together through the atmospheric path that you're traversing. All right, then the path radiance term, the LU term, is given over here. And what do we have? Well, we have the transmission from the jth layer up to the sensor and up through the atmosphere. All right, now for J, where do we start J from? Well, we start J from the layer above where we're currently looking. So if we go back to the illustration here, if there's 4 layers here, let's say 1, 2, 3, and 4, if we're worrying about this particular path right here, we would start J at not 1, not 2, but at 3. So we go through layers 3 and 4. And this one's just layer 4. This is layer 2, 3, and 4. And finally, starting from the ground, we would go through all 4 layers. Okay. So we wind up with the transmission for each of the layers, the radiance from that layer, times that transmission. And that radiance, that black body radiance for the particular layer of the atmosphere, which is based on its temperature, is multiplied by 1 minus tau, or the emissivity of that particular layer. So you're treating the atmosphere as a black body. You modify that black body assumption by the emissivity. And in this case, we just use emissivity 1 minus transmission. And then you multiply it by the transmission through the rest of the atmosphere. And you do that for all the layers in the atmosphere. Does that make sense?
So that term is all the LUs that we were looking in the previous diagram.
This whole term here is the LU term.
And the first term is just a...
This term right here, this product, is the transmission term. So if we look, we just write it down here, right?
Yeah, that one.
This one is the temperature of your target on the ground.
Start.
So this is your ground, emissivity of your target on the ground, times your transmission, which is that product, plus your path radiance term, which is the summation over here. So just in case you were wondering what's going on when you're on Montran, I mean, these are the computations that happen. You look in your Montran output and you have this table of output as a function of wavelength. Right? So what you're seeing there are all these terms as a function of wavelength. So the plots that you're making from the first 2 runs of Montran that you do are all these terms right here. So you'd be able to actually take this equation and implement it using the data that comes out in that spectral table. Montran does that for you and gives you this final value down at the bottom. That's that integrated total radiance, depending on how your sensor's oriented. All right. Now, once you have that radiance, that's the radiance reaching the edge of the atmosphere, you then need to go ahead and modify that based on the spectral response function of the sensor, right? And integrate it over the bandpass. that you're looking at. So our prime here, so theta, is the sensor spectral response function, integrated over the bandpass that you're looking at, and that'll give you the final effective radiance reaching your sensor. So in the current laboratory, again, that's at one point we're actually having you multiply your spectral terms by the spectral response function of Landsat 4, I'm sorry, Landsat 5 band 4. So that's essentially the step you're taking in the laboratory right there, figuring out what that bandpass radiance would be for that particular. Does that make sense?
Can you just go back to the
Absolutely.
figure where with the diagram?
Yep.
Because I'm trying to visualize what we're saying with that formula there. So we're actually calculating transmission. So when you're looking at a specific layer and looking at the transmission of it.
Yeah, let me see if I can get, oops, let me see if I can get both of them on the screen here. There we go. Do I have any clue when I put 2 on here?
Just do a print screen and then put it in paint.
Do what?
Do a print screen and then copy it into your paint window, and then you can just, you know what I mean?
Yeah, sure. You know the keystrokes to do a print screen?
Yeah, don't you have grab? That's the easiest thing to do, I think. If you grab it, you don't even have to copy. Just go up to your top right where the little magnifying glass is. No, the very, very top right of your screen.
Oh.
You know what I'm talking about? Like the actual file.
Please take over.
What are you running?
It should be snow leopard. Yeah, I mean there's no
Yeah,
spotlight up there.
the grab should be in your you need to just capture the selection. I don't have it open.
Thank you. All right.
Okay, so I'm trying to visually relate those two terms and what the first term is graphically versus the second. So the first term.
So which, you want to look at this term here?
Yeah.
All right. So the transmission from the I=1 layer up through N, so that's all the layers in the atmosphere, right? Is this transmission through this layer right here,
Yeah.
times the transmission through this layer here, times the transmission through this layer here, times the transmission through that layer there. And so it's simply the product of all of those. Imagine you had 3 pieces of photographic film and you stack them on top of each other. The density would increase because you stacked them, right? And the transmission would decrease because you stacked them. So the same thing's happening here. You're just treating it as if this were 3 pieces of film with 3 different densities and stacking them on top of each other. And if you have so many photons coming in to go through the first layer, you multiply the transmission of that layer, you have the number of photons times tau, then you multiply that product times the transmission through the next layer, and so on through. Okay. Now the second term here is, so LTI lambda is the black body transmission, I'm sorry, black body radiance for the ith layer. So this layer right here, this layer right here, that layer right there. You multiply that by the emissivity of that layer. Now you know the effective radiance leaving that layer. Then you take it through all the layers above it, so you need to attenuate it by the transmission of all the layers above it, so that's the product. And then you need to add all those individual layers, that vector, that vector, that vector, that vector, together. That's that summation.
I just wasn't clear because I couldn't tell whether I was increasing or decreasing on that diagram I was done.
Absolutely. So yeah, this would, I equals 1 down here,
Okay.
I equals n to the top. All right. So, multiply by the response function, we have our effective band radius. All right, now, that gives us tau, that gives us LU, right? And that's two of the terms we need, but we also need LD. Okay? So, if we go ahead and, just like you're doing, it's almost like we're making you do this lab for a reason. Just like you're doing in the lab right now, if you went ahead and you ran Modtran again, and this time, rather than being in geometry where you're looking down at the ground, you take your sensor, you bring it down to the ground, and you look up. Right? So essentially, you're looking through all the atmospheric layers to space, and you can do that at all different angles. And by doing that, you can come up with this term right here, LD theta phi. Right? This is just when you're looking in a particular direction in azimuth and in elevation, or declination, depending on how you define it. That would be the radiance as a function of wavelength. Right? Modtran will give you that as a function of wavelength coming down from the sky at that particular location. Now, what is that? Well, that's the summation of all those layers and the radiance coming from all those layers, but now, rather than propagating up, they're propagating down, okay, towards the ground. So wherever you put your sensor, Modtran would know which way to traverse through those layers. So saying I goes from 1 to n going up is true when you have an upward-looking sensor. But if you have a downward-looking sensor, I'm sorry, when you have a downward-looking sensor, that's true. When you have an upward-looking sensor, those indices would reverse. All right, so what we wind up doing is looking over that hemisphere at all the different angles, converting that to irradiance, taking that irradiance and correcting it geometrically for its projection onto the ground, and then multiplying that by our step in angle that we're looking at. Obviously, we'd like to look at this at all possible locations, right? So this was a continuous interval, but we wind up doing this as a discrete interval because it's just a number of runs. I mean, you wind up, I think you're doing about 84 runs of Modtran, and that's going in 15-degree increments in declination angle and 30-degree increments, I believe, in azimuth angle. Right? And that's fairly coarse. I mean, you probably want to do more than that if you need a very good estimate of what that atmospheric downward radiance does look like. All right. So just pictorially, what you wind up doing, you're looking at a particular point in the sky and over a particular solid angle. So that's the interval that you wind up working through.
Never really thought about it until just now, but just pictorially, like if we flip this hemisphere up so it was actually more or less what the sensor was looking at, there's parts of the atmosphere that were not covered by Newton's technique, right? So the scattering that's going to hit the sensor is not going to be like this hemisphere. It's actually going to be its hemisphere.
Remember, this is what you're doing here is downwelling radiance. So if you let me make sure I understand what you're saying. Are you talking about the actual sensor that you're doing your remote sensing collection with, or the sensor that you're measuring the downwelling radiance with?
The sensor you're doing your collection on.
Okay. So the sensor you're doing your collection with is located up here somewhere.
Mm-hmm.
The target on the ground is what's receiving the downwelling radiance. So you want to sample the atmosphere above the target. Right? It really has nothing to do with the sensor at this point. It's just what hemisphere is the target exposed to at this point.
But I think that what Maria is asking is that when we are looking at the upwell radiance, we're only considering like the vertical component of the radiance and not all the angular components.
Yeah. Absolutely. Upwelling radiance is different though. Right? Upwelling radiance is the radiance propagating from the atmosphere between your target and the sensor. And it is only along a single path.
Okay.
The downwelling radiance is all of the skylight that's incident on your target and then reflected through that same path to the sensor.
But at this point, we already have radiance reaching the sensor, right? That was the
You do
equation.
have radiance measurement sensor, which is a combination of all these other things. So why are we doing all this to begin with? And if we go back to, let's go back a couple here. Go back to the propagation equation. All right, yeah, let's say it's this term right here. So we measure this term with the sensor. With Modtran, we can figure out LD by doing this hemispheric integral. We can figure out tau. We can figure out LU. We can measure the emissivity of our target, or we know the emissivity of our target. Right? So what's left in this equation? This is the only unknown term. Right? So the idea of the remote sensing exercise that we're doing here is if we have a sensor and we're looking at the ground, we want to know the temperature of an object. Right? So since this is our only unknown, we measure this, we figure everything else out from Modtran or measurements. Now you can invert this equation, solve for LT, and as long as you know all the other terms, that LT is going to really represent the temperature, or the radiance due to a black body at a particular temperature. Invert the Planck black body equation and you have the temperature for your target. So again, that concept is, you make a measurement at your sensor, you have to know everything else that's going on in that propagation equation to come up with the one observable that you really, really want. Right? And that's probably your temperature, your target.
So this is just like you were saying with the pool experiment. You want to figure out the radiance and then get to the temperature.
Exactly.
Okay.
You have just a different way of coming up with the terms. With the pool experiment, you have data in your scene that you know the radiance for. Right? And if you know that, then the atmosphere really doesn't matter anymore because it's going to come out and be contained in those slope and the intercept terms that are there. And you can back out your value. Now, what's not true about that statement, though, is if your target's not a black body, you got to worry about the downwind radiance still.
One question there. So in here, you integrate the previous equation in the phi.
This one right here? Or-
Right.
Yep.
But LD is still a function of phi. So how come? Or is it assuming?
This goes back. Okay, so the phi does drop out. All right. If you go back to last quarter radiometry, you did the magic pi computation at some point. Right. This is that magic pi computation. Remember, the phi does drop out of that equation again. It's not. It's only a function of elevation angle and not the azimuthal angle. Once you work through all that. I hope Emmett derived that with you guys. I mean, there's a long derivation that comes up to this point. So if you check back your notes. If not, I mean, I can go through that with you.
So,
Sorry.
so that equation right there, that,
This one.
no, sorry, the propagation equation?
This one. Yep.
Propagation. That is essentially the same as the one that you were showing for Modtran, except that with Modtran, we're assuming that we have a black body. So we don't have the downwind.
Well,
Because you just.
With- let me go back to this one. So right here, there's no target again. Right? The downwelling is just the energy reaching this point on the ground. You can put any target you want here. But if you're in Modtran and you're doing the computation of the radiance that's coming from this point in the sky down to the ground, in other words, you put your sensor down at the ground and you look up, right? There's no target involved. You could put a target in place, and if you look at the card deck, I believe the surface albedo term goes to 0, indicates your downwelling radiance computation. Surface albedo is the equivalent of reflectance. 0 meaning, 0 becomes a black body, so it treats the atmosphere as a black body. So once you get that LD term, it is just a single term here. This is the integral of all those radiance values, or irradiance values that you measured as a function of angle around that hemisphere. Right? Then you can go ahead and put whatever target that you want on the ground, and it would have that reflectance.
Can you go back to the Malvern?
That one? There's so many.
It was the one that had the products on the side. Yes, that one there.
Okay.
So that one, that's the radiance reaching the sensor
That is the radiance reaching the sensor for a black body,
for a black body.
because there's no reflected downwelling term. It's just the energy due to the black body propagated, transmitted through the atmosphere plus the path radiance term. What's missing is that reflectance times the downwelling radiance term. So this was to get tau and LU. You can assume black bodies and do that, and then turn the sensor around, get LD, and then you finally have enough information to solve the equation. No, it's not until this point that you can solve it, unless you have a black body, because then this term just goes away. All right. Now, in order to do this successfully, you have to know what the atmosphere looks like. Right? So, I mentioned last time, Montran has several standard atmospheres in there, but what we hopefully have is a measurement of pressure and temperature and actually water vapor concentration as a function of altitude in the atmosphere. And these are called radiosondes. That data can be input directly into Montran. It's a series of card decks. It actually takes the file that you have and puts, however many more lines in there, as many layers as you've defined in the atmosphere. Most of the time we get, on the order of about 30 different layers in a radiosonde. So that file just increases by 30 rows, and in each of the rows are the altitude that the measurements were made at, the pressure at that altitude, the temperature at altitude, the water vapor concentration at that altitude, or relative humidity, depending on what measurement you get. And these are typically the shapes that you see, but the shapes change, all over the place. For instance, temperature typically decreases as you go up in the atmosphere. Right? Pressure usually decreases as you go up in the atmosphere. Right? So usually these plots, if you plot them altitude on the vertical axis and the parameter that you're measuring on the horizontal axis, you'll always see them leaning over to the left a bit. But things get a little weird as you get near the ground. Right? And so, for instance, temperature actually, can decrease, as you get towards the ground, and it could increase as you go up a little bit in altitude, and then continue to fall off as you go down. And it's very hard to make this measurement at the time of your collection, which is what you really want. So you will often see that, for instance, early in the morning, you go outside, it's usually cold, and then it usually heats up pretty quickly. By 10 o'clock in the morning, it's not as cold as it was when I woke up, unless you woke up at 10. Then at 12, it's not normally as cold as when you woke up. So these measurements, though, these radiosondes are normally launched at noon and midnight UTC time. So it depends, where you are in the world when they're launched. And what you want to do is, go ahead and take those measurements, and the atmosphere is pretty stable above some altitude, right? 0.5 kilometer, 1 kilometer high. Above that, the atmosphere usually doesn't change all that much as a function of the time of day. So you're pretty safe using that radiosonde data, from maybe 0.5 kilometer up. But the last, couple hundred meters, you want to be careful of, right? So the local value, if you know the temperature at the time of your collection, oftentimes what we wind up doing is we wind up doing a correction of that last layer in the atmosphere to change the temperature of that layer to match what a local met station might have measured at the time of your collection. So something you want to keep in mind if you ever start to do this kind of thing is that you can introduce some pretty dramatic errors in your data, because where are the most molecules in the atmosphere? Well, they're down here. Right? Most water vapor, all of them are down at this level. So you want to make sure you get the pressure right, and the pressure is good. But the temperature, that's where you start to have a big problem. If you have a weather front come through and the pressure dropped between the time the radiosonde was measured and the time you collect, well then you want to correct your pressure also. But if the pressure dropped dramatically over that time, you're probably not doing remote sensing, right? Because there's some weather front coming through or 70-mile-an-hour winds like we had the other night. So you probably would be out there anyway doing it. So pressure and water vapor concentration are fairly stable. I say fairly stable when I say water vapor concentration, because you know that sometimes early in the morning it's a lot more humid than it is a couple hours later. So, but that's also a function of temperature, and that's a dew point, so it feels more humid. So by correcting temperature, everything else sort of falls into place for you. So you want to make sure that that bottom layer, typically we'll refer to that as a boundary layer, gets corrected for some ground observable. And if you could, you want to make that temperature measurement right at the site of your experiment. All right. So, emissivity. That's the last piece of the puzzle, right? We need to measure emissivity. So, back in the 1970s, there was this really neat string of literature that was going along. And there was a couple of investigators who were flying on board of an aircraft a carbon dioxide laser line scanner. Okay. CO2 lasers sit at about 10.6 microns, right? I mean, I guess that's the kind of laser that you use to burn holes through things, if you really want to do some destruction. And the nice part is what you could do if you put that in a line scanner and you actually illuminated the ground with the CO2 laser, and then you measured the return off that beam, you would get the reflectance of the ground. You know how much power the laser's putting out, you know how much power is coming back, you can measure the reflectance of the ground. Right? That's your emissivity. Right? So this image over here is actually a reflectance image caused by illuminating the ground with a CO2 laser and immediately measuring the return from it. So very similar to the way that a LiDAR would work. And what you get back is an emissivity image. So you have the emissivity for every spot on the ground. Well, this was the greatest thing in the world when I saw it, because we've been looking at thermal imagery for a very long time, and we never know the emissivity of everything we've seen. Right? Now you do. You had an image of it. Then in 1978 was the last paper I saw. Right? 1979 and on to this day, I've never seen another paper or anybody talk about this sensor. You can all speculate what might have happened. But I think a big part of it was you're shooting a 10.6 micron laser at the ground, right? That's not eye safe. Right? So I think these folks probably got in trouble more than anything else. You can think of all kinds of conspiracy theories, but I think what happened here is I don't think we're allowed to fly these things anymore. All right, so what do we wind up doing? Well, we wind up guessing at our emissivity. So we're right back to where we were. We have no system in place right now to do these measurements. So what we end up doing is having to go on the ground and measure targets, or know what targets are on the ground, and then look up things in handbooks. Or you can take a thermal hyperspectral sensor and do what's called temperature emissivity separation. Right? Because what does this sensor record? It records radiance. Right? Once you have radiance, that radiance is a combination of the emissivity of the target and the temperature of that target. So that radiance can go up or down if either of those terms go up or down independently. So you don't know if is it bright because the temperature is hot, or is it bright because the emissivity is high. Right? So you're always unsure. So there's a lot of techniques out there to do temperature emissivity separation based on hyperspectral data, and I'm not going to go over that today, but I will go over that with you guys because it's one of my favorite topics. But essentially, you wind up with, if you have a 100-band sensor, you have 100 unknown radiance values and 1 unknown temperature, and you can make a measurement with the sensor. You have 100 observations, and you have 101 unknowns. So it's one of those where you have one more unknown that you do observations. So you have to do an optimization to actually find your answer. So I will go over that with you. So we can form imagery like this today, but it's a lot more difficult than just using a reflectance measurement essentially to come up with that. But fairly successful. All right, so that's where I'm going to end with thermal for now. And we'll come back in a little bit when we start talking about hyperspectral data and look at how we can measure acidity that way. All right, so any questions on the thermal stuff?
So, in two steps, basically what you're doing is you're solving for your radiance by assuming that everything is a black body. Radiance reaching your sensor. Okay. Then we multiply it by a spectral response function of the sensor. Then we put the sensor on the ground to measure the downwell radiance. Okay, and then just to switch the orders, we figure out what the emissivity is, doing temperature, emissivity, separation, and then we plug that all into that standard equation to solve for L sub T.
Yes.
Okay, but I think the thing that I'm confused about is we're saying, are we assuming the target is a black body or not?
No, you're assuming all you're measuring is radiance. Right? You don't know if that radiance is from a black body or a gray body or
Right.
Very
So
long distance.
how do we convert L sub T to a temperature if we're not assuming a black body? Because
Okay.
if it is a black body, it's easy, right?
No, you agree. You're absolutely right. One of the last things you do here is you divide by epsilon. You divide by your emissivity. So once you divide by that emissivity, you increase this LT term, or the term that's left over, and now it is the radiance from a black body. So let's say there was no other terms in this equation except the radiance on the left-hand side and epsilon times LT. LT equals the radiance you measured divided by emissivity. So it then is a black body radiance. This is a black body. Multiplied by this is a gray body radiance. Take gray body radiance divided by epsilon, you get black body radiance.
So is the LH theta, that's the radiance reaching the sensor?
That's the
right?
radiance recorded at the sensor. Yep. So if there was no atmosphere in the way, all you would have is radiance reaching the sensor is the black body radiance leaving the target times the emissivity of that target.
So it seems like we are saying that the target is a black body. It's like we are, but we aren't.
In the end, you are.
Okay.
Right? In the end, you are, because this is actually the target leaving radiance right here. So the target is not a black body. But if I take that target leaving radiance and I divide it by the emissivity,
Oh, then
what I
you
have
can't
is the
see it.
equivalent
Okay.
of what would leave a black body. That make sense?
Yeah.
All right. So to switch over to the reflective part of the spectrum, right, there's a couple things change. Here our equation, obviously, the big equation, all the terms are still there, but different ones become more important in this way of infusion. So the temperature of the target and the emissivity and the things we've just been talking about, take a back burner, but now the reflectance of the target and the exoatmospheric solar radiance and the solar radiance reaching the ground all become important. So if we wanted to go out and we'll kind of approach this in a similar fashion to the way that we did thermal, let's start by doing the most fundamental and the most accurate sort of calibration that you could do, which is actually putting known reflectance targets on the ground in your scene. Right? So if I'm flying a sensor overhead, and I have the luxury of being on the ground where I'm at, I can go out into the field and I can put panels on the ground. And those panels can be prepared in such a way that I know their reflectance. So if I can have known reflectance targets in the field, and my objective in the visible part of the spectrum in the SWIR and near IR is to not do what we were doing in thermal where we're trying to come up with temperature, but here what I'm kind of trying to do is come up with reflectance, because reflectance is a physical parameter that I can use to go ahead and characterize what material I'm looking at, or the condition of the material that I'm looking at. Right? So that's where I want to get to here. So I don't want to get the temperature as we were doing over the past couple days, but I want to get to reflectance. So if just like in the case of thermal where I had some targets in the field that I knew their temperature, Here, I can know the reflectance of those targets and go through, very similar sort of approach. Now, the approach in this part of the spectrum has a name that folks use all the time. It's called ELM, or the empirical line method. And what that involves is having several panels in the scene, like I said, that you know the reflectance of, and then you can back out the reflectance of everything else in the scene based on that sort of data. So, these are panels that we've had out on experiments that we've done here at RT. This is actually out at Wright-Patterson Air Force Base on one of the runways. They actually painted very large targets on the ground, right on the runway itself. They actually painted resolution targets out there on the runway too. When I first got here, back in 2002, it's great when you're a new faculty member, you can kind of do whatever you want, and everybody kind of says yes to you for a while. So I went up to the president's office over in Building 1, and I said, can I go out in the parking lot and paint a 90-foot by 90-foot square on the ground and do one white, one black? He kind of looked at me and said, for what? I said, well, I want to calibrate the Landsat sensor when it goes overhead. He's like, yeah, go for it. So if you go down to the bottom parking lot, it's still there. It's faded, right? But 10 years later, it's still painted. I had two very sunburnt students at the end of that day, and I didn't realize that was going to be an issue. But it was a blast. They got to get this little machine, had a big paint canister on it. It sprayed paint on the ground. You got to walk back and forth and just, the things that they paint stripes with. And, oh, it's a blast. And then we used those as calibration targets. And they were awesome. They were 30 meters on a side. So when we flew WASP, what's the advantage of having a very large target on the ground when you're flying a remote sensing system?
Well, you can't miss it. And on top of that, it's not like you're going to have effects from reflectivity to the sides. So
Yeah.
you're pretty sure that you're going to have the reflectivity that you want.
Exactly. When you have a footprint on the ground, if I said, hey, I'm flying a sensor and it has a 1 foot footprint, everybody's first inclination is to say, okay, if I put a 1 foot target out there, I'll be able to measure it. That's not true, right? Because a lot of things happen that mess you up. So if I have a 1 foot spot on the ground and I have a 1 foot pixel that gets projected down onto the ground, well, that pixel is going to get projected right there. It's not going to be right on top of your target, right? What are the chances that it's going to be right on top of your target? It is 0, right? So, what's the other problem? These silly systems always have these things that are called optics, right? And they blur, right? So, if you really do have a 1 foot projection on the ground, well, that's true until you go ahead and you blur that, right? So this goes through some sort of an optical degradation function, right? So you multiply by the Fourier transform rate. You're all doing that right now. And what happens is the pixel grows, and it actually pulls in energy from all around it into that center based on some two-dimensional point spread function. So we'll draw something that looks like that, right? You have some sort of 2D blur function that occurs. All right, well, now I know I'm sampling too large of an area. So I'm pulling in some background, I'm pulling in my target, I'm not pulling it in all at a uniform rate. So you want those targets to be larger. So rule of thumb is that you want your target on the ground to be 3 times the footprint of your sensor. Right? Because if you've designed any sort of a quality system, your point spread function isn't going to be larger than 2 or 3 pixels projected onto the ground. Okay? And you should be able to hit the target with a single pure pixel. And that's the one you want to use. You only use one. You want your target to be 3 by 3, but you only want to use the best pixel, the one closest to the center. Right? And that's a terrible idea, because with all those pixels in your sensor, sometimes that might be a bad pixel. Or it might be one that you don't know the gain and bias perfectly about. You can have all sorts of problems. So what you'd like to do is you'd like to have a much larger target so you can get some number of pixels on target. Right? So the rule of thumb, 3 times the size of your pixel if you want 1 pure pixel. Okay? And as large as possible is really the answer. Right? So if you ever have the luxury of painting a 30 meter by 30 meter square on the ground, it goes a very, very long way to be able to help you out. Right? So targets dimensions are very important, but also the composition of that target is going to be very important too. Right? You want these targets to be as Lambertian as possible. Right? So when you look at them from multiple angles, you can understand the reflectance that's going on from that target. You'll measure the reflectance of this target. If you're lucky enough, you'll measure it on a goniometer, so you have the BRDF. Right? But the chances that you're going to have, number one, access to a goniometer is small. There's only a couple that are in production use around the country. And two, these panels, how big is this? This is 8 foot by 8 foot. How do you bring that in a lab and put it on a goniometer? Right? Well, typically you chop a piece of it off and you bring it back in and measure. The last thing anybody wants to do is ruin the target that they just made. So chopping a piece off isn't always an option. So a lot of times what you'll do is, if this is painted plywood, you might paint another piece of plywood at the same time and assume they're the same. Problem there is, as you use these panels over and over again, they'll weather, and your little sample won't weather. So you have to keep track of those sorts of things. When I was working for the Intel community, I worked for an organization called the CTAC, the Spectral Information Technology Application Center, and we had 30 foot by 30 foot canvas panels that we would roll out. We had 5 of them, and they were all different grade scales. So we had a white one, we had a mid-gray, we had a black one. We rolled these out at all our experiments. And for the first 3 experiments that we did, I was looking at data, and nothing was making any sense. Right? I was getting errors that I couldn't imagine. Why was this happening? It was just the error was way beyond what we thought we were going to see. It turns out that canvas, at some wavelengths, is transmissive. So you're seeing the grass underneath the panel through your target. All right, so we went back to the manufacturer of the canvas and showed them this, and they manufactured a new canvas for us that was opaque, right? But it's a very, very difficult thing to make a good target, right? So you got to be very, very careful when you're doing this stuff. Painted plywood is great, but paint's very delicate. If it gets dew on it, it's going to change. So you got to protect it like anything. Canvas is great, but canvas absorbs soil moisture, right? So your canvas gets wet over time. You got it. So putting these panels out, you're just going to be very careful. You know what you're doing. The best thing you could do is make measurements of those panels on the ground during your experiment, so you know the conditions on them. So take a field radiometer out with you, and then you can compare that field radiometer data back with the data that you measured in the laboratory, and make sure you have good data. All right. So once you have those things, let's say you've got some good measurements that you made, what do you do with them? Well, the empirical lab method's kind of simple. Here's your propagation equation. Simple propagation equation for a reflective region sort of target. You have your exoatmospheric solar radiance, divide by pi to make it radiance, plus your downwelling radiance. And this is actually the term that you're doing in the lab right now, in the reflective portion of the spectrum. You multiply that by the reflectivity of the target, diffuse reflectance in this case, times the tau up to the sensor, plus the path radiance. All right, so we got a nice linear equation if we arrange it this way, where m, the slope, is the summation of your skylight and your sunlight onto your target, and your tau2 term. Right? And your intercept is your path radiance term. All right, when is that true? Well, if I go ahead and I measure several targets at different reflectance values, and then plot them, I can come up with this slope, this intercept, and I'll have my LU directly, and I can back out my tau term if I wanted to out of this equation. How do I do that? Well, I have my exoatmospheric solar radiance, we know that. I have to modify that by the angle of the sun, right? So there's a cos theta term in there. So I can get that term. How do I get this one? Well, you do the modeling that you're doing right now in Montran, right? Get a radius on, get the right atmosphere in there, go ahead and run Montran a bunch of times, integrate over the hemisphere, you can get this term. That's one way of doing it. If you have a ground truth campaign, though, you can get a radiometer on the ground and measure that downwelling radiance. Again, that's not an easy thing to do, because a radiometer usually has some field of view, and it looks at just a portion of that hemisphere. Okay? So you'd have to put this on a, some sort of motorized control and scan out the atmosphere, very similar to how you're doing in Modtran now, but do it for real with a radiometer, and then integrate all those values. That's one way to do it. All right, so that's probably your best measurement you can make. They do make for radiometers these things called cosine receptors, which are essentially frosted glass domes that collect energy from all directions and focus that energy down onto the radiometer surface. Right? So that essentially is a hardware integrator. Right? It does the same integration that you would do by measuring radiance values at all different locations. This one measures downloading a radiance directly. And you can get, we have a field spectrometer by a company called ASD, and they make that cosine receptor for the end of their probe. So you can actually just stick it out in the field and measure spectral download radiance. All right. So once you have that term, you can then back out tau 2, and now you have all your atmospheric components. You can measure this one. These are known from tables. This one is your intercept term, and tau 2 you would solve this whole equation for tau 2 and come up with your answer, provided you knew the reflectance of your target on the ground and you had some known panels in the scene, so you're all set. Sounds easy, right? All right, so remember here that you could even go a little bit further with this. Once you have tau 2, you can come out with the optical depth of your atmosphere, if you wanted to. And so you can solve for the delta term right here. All right. Questions on that?
So, we're trying to get tau, or we're trying to get the reflection?
Well, yeah. All right. So now, if I'm calibrated, if I come up with LD, and I come up with tau 2, and I come up with LU, how did I do that? Well, measurement derived from multiple observations of points, make it a plot, come up with the intercept. I come up with n from that same plot. I know these values. I can measure this value. I know R for my target, my calibration target. So now I can come up with tau 2.
Oh, and
Once
then
I know
you can
tau
apply
2,
that throughout the scene.
once I know tau 2, now I can go ahead and figure out the reflectance of every target in the scene. And so you got to get all your parameters first from things that you know, and then you can use those parameters across the scene, assuming that the atmosphere is constant across the scene. For narrow field of view sensors, that's a pretty good assumption. When you use something like a Landsat sensor, obviously, when you're looking at tens of kilometers, not as good of an assumption. All right, now, that shows that the radiance is linear with reflectance. If you design your sensor properly, do all the electronics properly, radiance is going to be linear with digital count also, through some gain and bias, electronic gain and bias. So you can go ahead and you can rewrite that equation. You're substituting in for L everywhere. And what you can wind up with is just another linear equation. And it's just a transfer equation. So the primes on here indicate that you can relate digital count directly to reflectance, if you wanted to, through M prime to B prime. So exactly the same solution as before, but you can just go directly from digital counts value, so you don't have to go through this calibration step on your computer. Yeah, that's just a convenience. It used to be that you couldn't hold floating point images in any sort of data type, and this was important. But now they can hold floating point images. Just take your digital counts that you record on your sensor, convert them to radians, and use your previous equations that you saw. Okay. So, how do you do this for big sensors? How do you do this for satellite-based sensors? Well, in these targets, back here, you can imagine yourself going out with a field radiometer on your back and measuring that target. Right? You might even get on a ladder and get a big footprint on that target and get an overall integrated value for the radiance to the surface. But when you have a satellite like Landsat, where its pixels are 30 meters on the side, you can hope to have some big targets like these that painted out right pad, or the ones we used to have here. But the folks who do that calibration, I mentioned this last time, that the folks who normally do that calibration will glance out at the University of Arizona, and they have the great fortune of having these, you know, beautiful flat areas that are all stained ground cover type, right? Either a salt flat or a sand flat out there. Now, over a 30 meter by 30 meter area, how convinced are you that these targets are uniform reflectance everywhere? You know, I don't care what you're looking at, the reflectance changes. If the reflectance was the same, it would look like this, right? Everywhere. Where have you ever walked in the world where the ground has looked like this? All one reflectance value. There's always some variation, right? So to account for that variation, all you need to do is you need to make many, many measurements. So when we go out and we do an experiment, let's say we measure it over a football field. We've done this in the past. We've gone up to Irondequoit High School, and we've had students walk that field with a radiometer, right? So you're kind of like it's kind of like you're in high school band again. You're walking across the field, making a measurement, making a measurement, making a measurement, making a measurement. Walk back across the field, move down 5 yards, make those measurements, and then go up and down that field, and every 5 yards make another set of measurements across the field. So you have hundreds of measurements made across the grass, and you come back with, and you can do whatever you want with those. You can integrate them spatially, you can integrate them all together. You can then spatially use that data. So the folks out at U of A, this is Phil Slater, who's long retired, but he built this thing that he actually called a reflectomobile, which was a little trailer he dragged around the back of his pickup with a radiometer hanging off the back, and he would just take measurements driving across the dry lake beds and sands that are out there. And these were great things to be able to do. My guess is he did that once, and then grad students do it after that. All right, so coming up with these parameters now when you don't have ground truth is a very difficult thing. All right? You can have ground truth panels like we talked about. You can have large uniform targets and make sure you measure the heck out of them so you understand them. And you could do collections that way. But more often than not, you don't have either of those luxuries. You don't have that in-scene target that you really know. So coming up with a calibration in the reflective part of the spectrum based on just in-scene data turns out not to be as easy as it was in the thermal infrared. Right? So we're going to sort of approach this in a piecemeal sort of fashion. Now, one of the things that people have been looking at for quite a while, and if you look at the earliest papers on these, they're back from the early 1970s. There was a couple of investigators who were actually lived over in Buffalo, had a small company there, Ken Peach and Johnny Walker. Believe it or not, this guy's name was Johnny Walker, just like the Lincoln. And I think he was intoxicated most of the times that I met him. These two guys were great. They were early pioneers in remote sensing. I had a really good fortune working with Ken Peach on a couple of projects early on in my career. And he was just an extremely smart, very resourceful kind of guy. And they came up with this great idea to try and characterize what the upwelling path radiance was going to be in a scene when you had no on-ground targets, no calibrated targets, no ground truth at all. And they came up with what they called the shadow method. You'll often hear it called the Peach and Walker shadow method, named after those guys. And what they wound up doing was they said, okay, when I stand in a shadow, I can still see I'm illuminated by skylight. Right? When I'm out in the sun, well, I'm illuminated by both skylight and sunlight. Okay? And knowing that, they went ahead and just wrote out the propagation equations from there. So here's the radiance in the shadow. Right? What's the radiance in the shadow? Well, it's your F. Remember F? That was the fraction of the hemisphere. That was sky. Okay. So if F turned out to be 0.8, that was 80% of your hemisphere was sky. So some portion of it, some small portion might be blocked by a building. Times the downwelling radiance, right, that you measured over the entire hemisphere. times the transmission through the atmosphere times the reflectance of your target. Right? So you had your energy reaching the surface, LD. You modified that by how much of the hemisphere was actually sky. You reflected that off your target, RD, and then you multiply that by tau 2 to propagate that energy up to the sensor. Right? Then you also add in LU, right? Because the path radiance makes up part of your signal. All right, well, the same thing, you could do the same thing for a point in the sun. Right? So they measured a point just inside the shadow of a building and a point just outside the shadow of the building. Right? So the shadow method involved making those two measurements. All right, well, what did this one outside look like? Well, it looked just like the one above it, except that you added in the exoatmospheric solar radiance reaching the ground. And then that would also get reflected off the target. Right, so that was the only change in the equation, the addition of that. All right, that makes sense?
Are they making the same shape, using the same shape factor value because
In and outside of that shadow?
Because
It's ever so slightly different.
But
Yep.
your error will be very small if it's just inside the shape.
So they went just inside, just outside, and assumed that F stayed the same. And they assumed the material was the same also. All right, so let's say that was a concrete pad next to a building. And the concrete here and the concrete there was the same, and F did not change the thing. All right. Now, if you, I don't want to jump there yet. So, at that point, what do you know? Right? Well, you know your measurement values. You know F. You can estimate F. You got to look around you and figure out what portion of the sky. It'd be nice to measure that, exactly as you can. You don't know tau. You can know R. You don't know LD. You don't know LU. So you have a lot of unknowns though. We have two equations here. So what do we have? We have one unknown for LD, one unknown for tau 2, one unknown for LU. So 3 unknowns, 2 equations. So that's not quite what we need to solve the problem. All right, so how do we go about doing this? All right, so the radiance of the bandpass observed just outside the shadow edge is just like we talked about right here. And when you cast that onto a diffuse reflectance material, right, so this again makes some assumption about the material that you're looking at just inside and just outside of that shadow, that it's diffuse. Right, you wind up with the L in the sun being this and L in the shadow being this from the previous slide. All right, so combine those two equations by solving on the one constant. The constant between those two equations is RD. We know that's not going to change. It's the same material. Right, so equate these based on RT, and we wind up with an equation that is L sub S, the measurement that we made in the sun, equals this mess over here on the right-hand side. All right, well, what do we have? We have the exoatmospheric solar radiance. We have the downwelling radiance. Here we have the measurement that we made in the shadow. And then the same term over here that we had over here, times the LU term plus LU. So that's what it works out to be. Beautiful thing again. If you call all this your slope and all this your intercept, you have a nice linear equation. Okay? So we're not real exotic people here in one sense. Everything always reduces down to a straight line. I don't know if you've noticed that so far. All right, but in this case, our slope is this term and our intercept's this term. And if I measured several different targets inside and outside of shadows that were of varying reflectance values, so I went out and I measured some asphalt inside and outside of a shadow, some concrete inside and outside of a shadow, some grass inside and outside of a shadow, as many targets as I could measure in a scene. And if you look at a typical scene and you have good enough resolution, it's key that you have good enough resolution here to see shadows. If you have that, you're going to see shadows everywhere in your scene, and you're going to measure points inside and out, as many as you could. You plot those against one another. The radiance in the sun, radiance in the shadow, plot those against each other, and you come up with your slope and your intercept for that term. So once you come up with that slope and intercept, check this out. You can immediately back out LU, right? If you know your intercept value and you know your slope, solve this for LU, which is just B over 1 minus M. You have your Ruffeld radiance value. So just from making some in-scene measurements, you can come up with that term. Now, how about this term? What do we got over here? You got your exo-atmospheric solar radiance, which you know, downwelling radiance, which you don't know, and F, which you can estimate, so you can solve for your downwelling radiance. Right, so using these simple measurements in the scene, you can solve for LU, and you can solve for LD. Now, one of the other things that they come up with is this thing they call the skylight to total illumination ratio, which again is a function of, it's just your L sub S term over your L sub SH term. Oh, I'm sorry, other way, reciprocal of that. And they define that in their paper to be this term they call little l. Now, the one thing that's missing here is tau. And that's the one thing we don't know. Right? And there's really, you go back here to this equation, where did that tau wind up going? Well, once you went through all the arithmetic, unfortunately they all canceled out.
But at this point, we know L sub D and we know L sub U, and now we have two equations and one unknown, so can't we solve for it?
That's exactly what you wind up doing. So you wind up with this point with just one unknown and two equations, and you can solve for tau 2. So being able to from measurements, know LD and LU, you can then go ahead and solve for tau.
But RD, you know from tables? Or
RD, you'd have to know, right? You'd have to know, you would have had made measurements on the ground, or you say, hey, that's asphalt, I know the reflectance of asphalt's this, or it's concrete, I know the reflectance of concrete's that. Those are all lies, right? Because the minute you lay concrete, it starts to oxidize and change.
Right, but here you have two equations, and you can solve for two unknowns, right? You can solve for tau and RD with just like
Yeah, you should be able to. I've actually never done that. But yeah, you should be able to do that. Very good. All right, now, there's a lot of other, whoops, one sec. There's a lot of other things that were spelled out in Chapter 7 for reflective. And just check one question here. Is there such a thing as bidirectional effect in the city function? Oh, I'm sorry, Greg, you had a couple questions here. Is there a high tran? Well, there was a low tran, there was a mod tran, there is a high tran, right? And it's the high resolution transmission database. And it's truly just a database of atmospheric measurements that were made by the Air Force Research Labs. So the high tran database is actually built into ModTran. Is there such a thing as a bidirectional emissivity distribution function? Absolutely. And it can be measured. There's a couple goniometers out there that do measure that function directly. They measure it as a reflectance, and then they use reciprocity to convert it to an emissivity.
The thing that you said that I'll roll down now, you have two equations.
Oh, okay. All right. So we wind up with two equations, one in the shadow, one out of shadow. We have two unknowns in there, tau and RD. So if you have those two equations and two unknowns, you can go ahead and you can solve for tau and RD explicitly. Okay, so like I was saying, there's a whole bunch of other things in this chapter that are very obscure, very seldomly used. In other words, over a almost a 30-year career now, I've not used anything else in this chapter. So I'm gonna leave it for you. You could read it if you want to. You can read it sometime in the future if you start to do some calibration in these areas. And but again, it's some really interesting material, but it's stuff that's not used all that often. This technique right here, actually, when I was working for NGA, the National Geospatial Intelligence Agency, I was part of I was heading up a group that did evaluation of models. Right? So I was in charge of setting up all kind of ground truth experiments, writing physics-based models to look at certain parameters, and then come up with solutions that would help analysts analyze things that they were seeing in the scene. And I was also, as part of that responsibility, I had to look at models that other people produced and supplied to the intelligence community to do these same sorts of things with. And so I got this model one day from a company, and what was it? Well, it was something to look at reflective imagery, and it came up with LU, and it came up with LD, and it came up with transmission from making measurements inside and outside of a shadow. So it was a nice interface. You clicked inside and outside shadows, and up came all these atmospheric parameters, and then it made a reflectance image for you. And I was like, huh, I've seen that somewhere before, right? So it took me 2 seconds to remember that Ken Peach and Johnny Walker had done that, and this company had just charged the government $1.5 million to deliver this product to them. I just talked about it in what, 10 minutes? How long would it take you to actually write this code?
I'm pretty sure that at an AMS conference, like a year and a half ago, someone presented this method.
As their own work?
I just remember them talking about it and people asking all kinds of questions.
Yeah.
They were making it seem like it was kind of new.
It was brand new. This thing has reinvented itself so many times, and people are presenting it as, this is a great idea, look what I figured out. And there's no references back to these early papers. Oh, so I brought that up at a meeting? The company was not happy. I knew it was the government at that point. So I don't know what happened. I walked away at that point. I just did evaluations. But, whoa.
So reflective calibration is pretty manually operated then?
Yes.
Okay.
And there's a lot, there are some automated processes out there to do these things, but in general, they don't work all that well. ELM is still the best one out there that you could do, but it requires you to have targets on the ground. This shadow method is a fantastic one, but you're right, you have to click a bunch of points. If you can write shadow detectors, which there's plenty of, then you can go in and you can pick points inside and outside those shadows pretty easily, just doing some image processing, but then you got to know the reflectances of those, or maybe you derive those points.
Do you say ELM is scene specific, or can you use it for multiple scenes within like a given area, or what?
No, it's scene specific, because as you go to another area, your atmosphere can change. Right? So if you have some confidence that you have a nice uniform atmosphere, perhaps over a desert sort of scene, then you might be able to use it in several scenes in geographic proximity, but I wouldn't extend too far away.
Would you ever do something like this for like a really low resolution sensor?
Which one? ELM?
Yeah.
ELM, yeah. That's how we're proposing doing a lot of the calibration stuff for Landsat, is to use big uniform reflectance areas.
But I mean like for MODIS or something like that, because the atmosphere is going to change a lot more for MODIS than for Landsat.
Absolutely. So pixel by pixel calibration techniques are good, but they're very difficult to carry out. Because again, you have to have some sort of interpolated atmospheric observation to be able to come up with the parameters on a pixel by pixel basis. And there's a lot of techniques that will extract the water vapor in a column above a pixel. So that's one of the parameters that you need to go into Montran. It's hard to extract pressure from remote sensing imagery, but pressure is one of those things that maybe it doesn't change all that much throughout the scene. Temperature of the air column is a tough one for that. All right. So I'm going to skip through some of the slides here, and I'm going to head to this one. All right, so we looked at some in-scene techniques. We looked at some ground truth-based techniques. Now, this isn't a atmospheric calibration tool as much as it is, and what the title here says, a scene-to-scene normalization tool. But what the attempt here is to come up with a way to take a scene that you collected on one day and a scene that you collected on a second day of the same area. All right, so let's say I flew over the RIT campus on Monday, and then later on in the week, on Friday, I flew over the RIT campus again. Obviously, the weather's going to change, the atmosphere's going to change, and when you look at the imagery, it's going to look different because the transmission of half radiance terms will have changed over time. So if what your plan is to use that imagery to maybe figure out what things might have changed in the scene, well, you could make that imagery pixel by pixel lay on top of each other by registering it or orthorectifying it. Right? So now you have pixels that are in the same locations. And then you can subtract those two scenes, and anything that comes out to be non-zero is something to change. Well, there's a lot of things that can constitute change. It could actually have changed. If that's the kind of change you're looking for. The atmosphere could have changed above it, so it won't be zero, that difference. Okay? Or the actual reflectance of the target possibly could have changed. Right? If it was a grass, if you had on Monday, it rained last Friday, so the grass was nice and healthy on Monday, but we had really hot weather all week, and by Friday the grass was looking kind of dry. Right? That would change the reflectance properties of the grass. Right? But that's actually a real change that you might want to characterize. Right? But if the atmosphere is still in there and it's different, then it's going to mask those changes. Right? You're going to see changes when there aren't actually changes in the scene. So you could go through and atmospherically calibrate both those images, but you've seen the problems, right? It's either manually intensive if you're picking points in and out of shadows, or you had to run a ground truth campaign to convert back to reflectance. Right? You could do those things, and if you can, that's what you should do. But a lot of times, if you're just looking for change, if you can make those two scenes look like each other, or appear to have been taken through the same atmosphere, without actually knowing what the atmosphere was, then you could do change detection. So this technique, it's called, the general name for the technique is scene-to-scene normalization. John Schott, myself, Billy Volchek, and John Francis back in early 1980s, I guess, proposed this technique to the community, and it's really wonderful. I still get asked to review papers that they use this technique again and again, or it makes a modification to it. So as recently as last year, I just reviewed another paper that used this. So it's really caught a lot of traction in the community, and it's used a lot for change detection sorts of analysis. And it's really simple, and that's the beauty of it. All right, so imagine that you have reflectance on the ground, linearly related to radiance. Okay? And you have some term over here, which we call alpha. I don't know why we changed from M, but it's alpha here, and it represents a lot of things, right? That's the sky radiance and the downwelling radiance, the solar radiance and the sky radiance, and tau 2, and all that's kind of built into that term. And over here is the path radiance term, right? So if I knew reflectance and I knew radiance, and I was able to convert all that to radiance here, I can go ahead and plot data and come up with the terms just like we did previously. But I don't want to do any of that. All right, so let's rewrite this equation a little bit, where I'm going to take this radiance term, multiply by the gain and bias of the sensor, and convert it to a digital count. All right, so we can rewrite that by substituting this equation into this one. We can rewrite it as the gain of the sensor times this alpha term times the reflectance of your target plus gain times your upwell term plus another bias due to the electronics for the sensor. All right, so you can then go ahead and let's say we took two images on 2 separate days. All right, so the I term here refers to the day that you're taking the image on. So let's say we had an equation that looked like this for day 1 and an equation that looked like this for day 2. Okay? If I wanted to solve for day 1 in terms of day 2, right, what would that do? Well, first of all, that would convert all the day 2 digital counts to look as if they were taken on day 1. Right? And that's what we're referring to as a scene normalization. Right? Just change them all to make them look like they were taken on the other day. All right, so you can see that if you put all this together, you wind up again with a nice linear equation, right? Where the slope is this fraction right here, and the intercept is all this stuff over here. And a lot of different things in there, system level parameters and atmospheric parameters are all in here. But we wind up with this simple equation. So what that says is we should be able to come up with a linear equation that converts the digital counts on day 2 to look like they were taken on day 1. Okay. All right. Well, here's what goes on. If I had a histogram, right? I had an image, and I plotted the histogram of that image. If one day was very hazy, what would happen, and one day was very clear, what would the histograms look like if you looked at those for those images? What happens when it's hazy? What happens to the contrast in your scene? It goes down. And the overall brightness? It could go down or it could go up, right, depending on what kind of scattering is on it. I mean, sometimes when it's hazy out, you get an overall increase in brightness. So you could shift the histogram, but you're also going to squish the histogram. So the day 2 histogram, let's say this is the hazy day, it's plotted upside down here, apologize for that, is this thin histogram, and this black histogram here is the day 1 histogram, nice clear day. If I took the day 2 histogram and mapped it through this linear transformation, which I had on the previous page, I could spread it out so it sort of looks like the day 1 histogram. Now, this is a very common technique, I don't know if you've gone over it in DIM yet, called histogram matching, or histogram equalization. Have you done histogram equalization? All right, and then a logical step from that is if you convert one histogram to a uniform distribution, convert another histogram to a uniform distribution, you should be able to go through the middle there and convert one histogram to look like the other histogram, right? Well, it's a very nonlinear function when you do histogram equalization. It's just based on the statistics of the data and the cumulative distribution function for that data. But we knew we didn't want to do that because everything we've done to this point in time said that all these atmospheric effects are linear, right? So why let a nonlinear transformation come into play here? Let's constrain it to be linear, and we can come up with a transformation that we trust the physics behind a little bit more, right? So that's what we did. We said, hey, how did we come up with this line? All right, well, what do you need? Well, you need the slope of that line, and you need the intercept of that line. All right, it turns out, I think, down on the website, I think I put this out here for you. And here it is. Right, there's a little derivation here that derives these two equations which are just shown. So you can take a look at this. And it's just the radiance on day 1, the radiance on day 2. Here's their original equations. And then I go through here and come up with the slope and the intercept terms that we have on the next slide. Eventually. There they are. There's the slope term and there's the intercept term. Right? So take a look through that. But the important part in the end is here's the values. All right, so what did we wind up with here? We wound up with something extremely simple, right? What is sigma 1 and sigma 2? This is the standard deviation of the histogram on day 1. This is the standard deviation of the histogram on day 2. So it's just measure spread. What's this? This is the average digital count on day 1. This is the average digital count on day 2. Modified by that m term, that slope term. Right, so that's the slope and the intercept for this. All right, well, that's all it took. Right, you went through a couple pages of derivation, but in the end, it turned out that it's a very simple thing to compute. I have to compute a histogram of my data, come up with the spread, and come up with the means, and I can come up with the transformation function that I need right here, this linear transformation. All right, well, sounds like a lot of magic that went on there. It actually turns out it works really well. But there's a big assumption that's made, right? The targets in your scene could change. If the targets in your scene change, what's going to happen to your histogram? Well, it's going to shift. It's going to change shape. Right? Things are going to change there. So what you need is you need to derive this histogram, these histograms, not on your full scene, right? But on something that we wound up calling pseudo-invariant features, or PIFs. What a pseudo-invariant feature is a feature in your scene whose reflectance doesn't change as a function of time. Is there anything in the world that you know of whose reflectance doesn't change as a function of time?
Water and sand.
What's that?
Water and sand, maybe?
Water is going to change all the time, right? If bacteria, not bacteria, algae grows and algae doesn't grow, the reflectance of the water body is very dynamic. Runoff from a lake into a body of water, it's going to run off from a lake, run off from the ground, it's going to bring soil particulates into the water. So water is extremely variant over time. What was the other one?
Sand?
Sand. Sand get wet. The minute sand gets wet, it changes its reflectance.
So no.
Yeah, pretty much no. so the what it came down to was that the reason we called them pseudo-invariant features were we came up with an assumption that we made that may or may not hold all the time. So we always looked at you know, something like the town of Rochester, and in fact here's the images. These were Rochester images that we wound up working with, and we said that over time in a city like Rochester or any urban sort of an area, there's times when there's a new asphalt road put down. Right? Somebody's always putting in a driveway somewhere, somebody's always repaving a road, new concrete's being put down all the time, and then that concrete gets older and it oxidizes and changes its reflectance. The asphalt goes from a deep black to a gray to white, you know, with salt on it, and it changes. But as older asphalt oxidizes and new asphalt gets laid, statistically across a scene the size of Rochester, on average, these things won't change. So, what do you think? It's a problem. Maria, you said you hate probability, but if you thought about the probability of a reflectance occurring, and you plotted the probability density function of that observation, then is there always going to be dark asphalt? Is there always going to be bright asphalt? Is there always going to be asphalt right in the middle? Probably.
That means you have to subset your image. So now you need another technique to figure out how to subset all the asphalt.
Yep.
It's going to introduce more stuff.
Yep. That was my master's thesis. Was how to subset the scene out of asphalt.
Kind of seems like the example of using a city is kind of a moot point because it would just be so much easier to put some kind of calibration target in the city. But I mean, what you really care about is when you have places where it's like, what the heck are you going to use? You know, like when you're in forests and things like that. Like,
Oh yeah, this technique's not for everywhere. And a lot of the papers that come out over the years is how do you apply this to a forestry scene, and how do you apply it to an aquatic scene of some sort. And it's pretty much impossible to do that. And so this implies that you do have some sort of urban feature. Okay? So there it is, right? Automatic segmentation, urban features. It was actually really easy to do. I'm almost embarrassed that I got my sister this.
So the Center for Image Science was in published.
Yeah, we used to be in photography, which was kind of cool because we had a lot more students. Because a lot of students come to RIT for photography, so we were actually visible to the world. It was very hard for you to find us, wasn't it? I mean, you just came across us, in a search somewhere. Yeah, well, we used to be in graphic arts photography. We used to have 35 undergraduate students every year. Now we have 6 or 8. It's a little harder for us to recruit. But yeah, so I don't know. There's 3D plots just went by. Oh, yeah. And it turned out that when you plotted a ratio of bands 4 to band 3 in Landsat versus a ratio, or versus a band 7, and you thresholded those images, you formed a surface that looked like this all the time. And this saddle point right in here, if you could pick, it was right here, here's a large version of it. If you could pick this point right here automatically, it picked the thresholds that you needed to apply to these ratios, and then you logically combine those two images, and you came up with pseudo-invariant feature maps. So maps that looked like this, which were urban features. And it was very, very simple. Now, at that point it wasn't easy because it was hardware image processors and all that ugly computer stuff that we had to do, but worked out to be a pretty simple thing. All right, so you'll hear that referred to a lot as pseudo-invariant feature normalization. That's the one thing that, or one name that you'll see this by often. and it'll take a scene. This is a 1982 scene of Rochester. This is a 1984 scene of Rochester. And you can see that the contrast is significantly different. These were both early spring images. But you can see that you can take that 1982 image and transform it to look like the 1984, and you can see that these are horrible when they're projected. But if you look at the urban features in these both scenes, and you look at the histograms, they turn out to be identical after the transformation. And then you make the assumption that you normalize the atmosphere out, and you wind up with two images that you can now make a quantitative comparison between. So this would be, these are color infrared images, so you can see the bright red areas here. This image was taken later in the season than this image, so you can see the difference in biomass that might have existed at different locations during those 2 years. Okay. So I made up the exam on Tuesday, and thought about your question about can I have a formula sheet. All right, so a lot of what I'm going to ask you to do on this exam is I want you to go. How do you get ready for this? All right, go back and read through the beginning of chapter 7. I will tell you right now, it's all chapter 7 stuff. Okay? So
we don't need to draw the sensors or
no, not in this one. All right, so it's all calibration techniques. So as you read through the text, read through it carefully, and when you get at one point in the text, and you're reading along, and you see an equation, and all of a sudden there's a big jump to the next equation. Like, how did it get there? Sit down and just derive those. You'll get from one point to another. Right? Those big jumps that are there, they're just meant for brevity. Right? And I think, in most cases it's very simple to go from one point to another. But I'd like you to be able to derive some of these equations. So what I might do on the test is say, all right, starting with an equation that looks like this, derive an equation to figure out the upwell gradients, derive an equation to derive the temperature. And then I'll give you some data that you can plug in or you need to do something with. Obviously, we've done a lot of plotting one thing versus another to figure out slopes and intercepts. Right? So that's going to be the hardest thing on this test, is figuring out slopes and intercepts from plotting data. And so when you get to a point, you derive an equation, think about, okay, well, if I had these values and these values, figure out, just be comfortable with what you would plug in to make sure you can come to a solution for tau, let's say, or LU or LV. All right, now, we've done a bunch of different thermal techniques, so any of those are for a game, and we've looked at a couple different reflective techniques, so those are fair game. The other part I want you to do is just make sure, look over some of the stuff from last quarter radiometry, just so you're familiar again with radiometry. Or you can go back in the text here, chapter 4, I think, is where the radiometry review happened. And you can just give that a quick read through. I want you to make sure you understand, what is tau, what are extinction coefficients, what are absorption cross-section, what are those terms, and how do I combine these things? Just so you're familiar with that. So if I say, hey, what is the absorption cross-section, if for this particular atmosphere? Well, if you can figure out tau, then you can easily back out that if you knew the thickness of the path of the leak. So really just understand those definitions for the atmospheric parameters, like well, there's only one, transmission. So relationship between cross-section and number density and extinction coefficient. So beta, C, M, Z. Just make sure you understand all those relationships. And I think it should be pretty straightforward. As long as you can drive those equations, so fill in the blanks in the text as you're reading. We did some of those in class already. But there's other ones there, so make sure you can do those. And just feel comfortable that you understand what all the parameters are. And always look at units. Right? Make sure all your units are correct when you're doing any numerical computation. Because you'll get path lengths in meters, and then you'll get extinction coefficients in reciprocal centimeters and things like that. So just make sure you match up all your units when you're going through any numerical computation.
So you said to solve for temperature, and thus far we've always been getting to radians given of the black body temperature. Then you want to use, is it sigma 2 to the 4? Something like that?
Or just solve the Planck equation for heat. All right, so as far as the formula sheet goes, I would say, you know, you could have a sheet of paper. All right, with the formulas on there. So.
Size of the paper?
Ah. 8.5 by 11.
One side of the sheet, or?
Yeah, one side should be fine. And there's not that much stuff. Yeah, it should be fine. You didn't have size of the print, right?
Not good too.
Yeah, I don't want you to get stuck because you're, you didn't know the starting point. So you can have that stuff on there. All right, so short of that, this should be a fairly straightforward one, I hope. For this one, I'm actually going to be out of town, so I'm not going to use Blue Books. I don't know if you affectionately attached a Blue Book in any way, but I'm just going to give you a paper to solve on, and if you could just put all the paper together at the end, and don't staple it or fold it or anything, because I'm going to actually ask Monica if she could scan it, then she could send it out and I can grade everything. I'll come back on the plane and get back to you pretty quickly, hopefully. That's it. Any questions? Worries? Concerns?
Is there, this is a lot, but is there any way we could even just have like one example question that we could solve out? I mean, just to get a better idea of plugging in the numbers. 'Cause for some of these techniques, there's definitely like a lot of numbers that are going to be plugged in.
Yeah, well, I'm never going to give you a lot of numbers to do. I mean, it would only be, for instance, let's say we did a profile.
Okay.
If I gave you, data at 3 altitudes, and asked you to just plot that and come up with the value of the bottom, right? Where did it cross the grounding radiance axis? I'm never going to give you more than that. And all I'm going to ask you to do in that case is, give me an estimate. And so you're not going to have to fit a quadratic curve or anything to that. Just come up with an estimate of the crossing.
Right, so that is just reading the number from the graph.
Yeah. Draw the best line, see where it intersects, come up with a good value. You might not get the same answer that I got because you guessed a different value, but as long as you solved it correctly, that's all I'm looking for.
And the same for like slopes and y-intercepts.
Yeah. And let's see. So if we were doing a slope, actually, I would probably never give you more than 2 points to come up with a slope.
Okay.
Right. So then there's no ambiguity. Yeah. So it's not going to be a quantity of data that I'm going to ask you to push through. It'll just be the minimum amount of data that you would need to actually solve something.
Okay.
Is that
I think so.
okay?
And it wouldn't be like, so what were we talking about today? We were talking about using like the propagation model and just like, 5 steps. Do you want all the way through the 5 steps, or just like, let's get to this particular
Pieces
one?
of it.
Okay.
Most likely. Now I might give you 84 values and ask you to do the hemispherical integral by hand.
Where are you going to be again?
Yeah, I'm never going to tell. Cool. So if you come up with any questions between now and next week, or when that's going to, it's just I'll be in town until Monday afternoon, and then I'll try and get back to you as email as quickly as I can.
And no class or anything on Tuesday.
That's right, no class on Tuesday. I think that'll be okay. I think we're at a point right now where we're gonna do a little bit more in calibration as far as hyperspectral sensors go, and then we're gonna make a switch over to some image processing sorts of topics related to those. And I think we're on track. So I think as soon as Monday, we'll still be fine.